There you go. Hello, Twitch. Okay, now they can hear us. Okay. Sorry, guys. So, you didn't miss out on much, though. As I was saying, Software You Can Love, the final day is about thinking about the human systems that surround the creation of software, and also celebrating software a little bit as a form of art in on itself. And so, and also talking about how not only as software as art in on itself, but also how it can support the creation of art. That's also was an interesting topic from the last Software You Can Love in Milan. I love always pointing this out, but there's one talk that I feel like really nailed this point from Jeff Fowler, who is also here in the audience. I believe, Jeff, can you raise your hand? Oh, there he is. Yeah. So, yeah, please give it up for him. Man, can you think about it? We were in a very cramped room. I had one camera, one like table tripod. That was it. Now we're in a much better venue. Okay, so, but one other topic that I think it would be interesting to think about as software engineers that I feel like we don't think about enough is also a little bit the relationship between software and money, in the sense that, we are completely aware as software engineers how there's a relationship between, like information, for example. When something has a certain degree of complexity, you can simplify it past that without losing information, right? Like compression has limits, the concept of information. We are painfully aware of that. But the same is also kind of true when it comes to money and resources, in the sense that Software You Can Love cannot be obscenely expensive. At that point, it's not worth it anymore. And if you think about it, for example, let's talk about like the Zig Software Foundation. One of the things that makes the Zig Software Foundation and the Zig project interesting in itself is also the fact that it's run in a very lean way. Had this project been, like 100, 1,000 times more expensive, which is not actually that uncommon when you think about certain like huge companies when they try to attempt software projects, I would argue that Zig would be way less interesting, even just because of that. So obviously, you don't want to evaluate software strictly from the perspective of how cost efficient it is. But I would still argue that it's one of those mechanical truths of reality, just like you can compress data past a certain level without losing information, that you should always have in mind. So with that said, I would like to invite my first speaker, Joran Dirk Greef from Biodigital. So please, let's give it up for him. Yes, Dirk.
Yeah, we're on.
So, Joran, nice to have you here.
Thanks, Luis. So great to be in a cinema.
Yeah. So, can you imagine? Man, you were here for the April meetup, right?
Yeah, Milan party.
Yeah.
I keep trying to tell people what it was called. So it was like the pre-Software You Can Love or Milan party. Yeah.
Man,
2 years ago.
A little bit of a step up from there, I would say. Can you please introduce yourself for the audience?
Yeah, so I'm Joran, and founder and CEO of Biodigital. It was an open source project 2 years ago. And later that year, we spun out of Coil, who was our employer, and created a company around Biodigital to make it sustainable. Yes, that's it.
Yeah. Okay, so then I'm really looking forward to hearing your talk. Please, give it up for Joran once more.
Right. Yeah, grazie, Luis. So great to be with you all in Milan today for Software You Can Love and on stream as well. I believe that Software You Can Love starts with software you can trust. So it's hard to love if there's no trust, and it's hard to trust if there's no relationship. Because the best software is more than a program, it's a relationship between the makers and the users. Why we make software matters. So I want to explore the impact of this on our engineering decisions at Biodigital. For example, why we decided to invest in Zig. Why would you write a database in Zig in 2020? But first, I want to look at software in the context of relationship. Because I think if software is created in a vacuum, without thought for the users, or worse, at the cost of the users, it's not software you can trust or software you can love. So like any relationship, it's the thought that counts. And yet how often do we debate, as engineers, whether to optimize or not, or the color of the bike shed? All how, but no why. I believe it's because we're not always intentional enough as an industry to keep the main thing. Together we serve the users. Thanks so much to Andrew for putting that in the Zig binary. You write Zig Zen and you see it there every day at your terminal. You should go and do this exercise. Together we serve the users. Thanks, Andrew. But I think we so often sell our software short, even before we get to software, because so much of software is at the intersection not only of engineering, but business. So here I want to suggest to you also that perhaps we've got it backwards. So we tend to blame business for bad software. But what if our engineering is bad, not because we're too business-minded, but because we're not business-minded enough? So we ask the question, are we building a technology or are we building a business? As if the two are mutually exclusive. So you see, a question like this takes too small a view of business. And I want to encourage us as engineers to take a bigger view. So to understand for ourselves that good business is good engineering, and that good engineering is good business. So it's not just that business and engineering are about systems thinking. They are, but they've got this relationship between each other. They help each other out, actually, because crucially, the best software, the best business is not self-serving. So why we do business matters, because business is a relationship. It's a relationship between business and society, people serving people, with profit as a result of success, not a goal. So I love movies, and we're in a cinema today, and one of my favorite directors, I should have said Sergio Leone, but one of my other favorite directors, Steven Spielberg, once said, "I'm not really interested in making money. That's always come as a result of success, but it's not been my goal. And I've had a tough time proving that to people." And I think, this is because as people, we tend to think of business in the abstract. So let's get real. Can you imagine a Milan without business? So no cafes, no pizzerias, no gelaterias. That's all I do is when I come to Italy, it's like pizza a day, gelato a day, 2 espresso a day. That's my tourism. But let's just imagine that that's all gone. So all the shops, even the cinemas, we wouldn't be here today. And Peter Drucker, the business thinker, if you're ever in doubt as to, who you can point to for something authoritative about business, it will probably be this person, Peter Drucker, the business thinker. I think he captures this when he says that business enterprises are organs of society. So they do not exist for their own sake, but to fulfill a specific social purpose and to satisfy a specific need of a society, a community, or individuals. And as soon as I see this, I think that business starts to make sense. Baristas, bakers, and software makers exist not to maximize shareholder equity in the abstract. Let's get real. Ultimately, they exist not for that reason, but because it's beneficial for society to have people in the neighborhood pulling shots, getting up at 4 a.m. to bake bread, or staying up to write Zig. So if you're a cafe or a bakery, it's good business to serve good coffee or bake good bread. So why we do business matters, because business is a relationship. But the best relationships, they go further than trust. So trust is required, but you also want something more. Who we are, our soul, as business people, craftspeople, artists, matters. So if you believe that software is engineering, and also more than engineering, that it's all about people, then to make a human connection, you can't be a robot. You can't only be data-driven. You need X factor. So you need to have something to say, and you need to be able to say it. So like Joan Baez and Bob Dylan, when they used to go to gigs and they would watch different artists perform, some of the artists are just trying to, make some kind of hit. And Joan Baez and Bob Dylan used to ask each other, what are they saying? If you take all the style away, what is the substance? What are they saying? Which is also a function of why are they there? And so the best software to me, like art, it's the product of information, but also inspiration, reason, cold hard logic, but also experience, gut feel. People spend 20 years crafting software. You can't always articulate things rationally, but you have experience. And that's valuable too, subjectivity. And then precision, so easy as engineers, but also poetry. And I always think of Anti-Res, crafting Redis and the beautiful blog posts he wrote about that. I learned that from him, precision and poetry. So it's not only machine, it's man and machine, just like music. So you get a tight beat, the click track, and you get a rare groove. Words that rhyme and rhymes that break. Or as my favorite programmer, Kevin Flynn, likes to call it, biodigital jazz. And biodigital jazz is this intersection between business, software, and art. The remix you get when you see that everything is about others and that what you do matters because it fits into the bigger picture of life. So I want to share our experience of this in the creation of Tiger Beetle, an open source financial transactions database. And we were lucky with Tiger Beetle from day one, in that the purpose, the why, was clear. So there was a need. We saw this need while we were working on an open source central bank switch by the Bill and Melinda Gates Foundation. So it was a non-profit switch. The goal of the switch was to reduce the cost of making payments at a national level for countries where millions of people typically didn't have access to banks or credit cards. So they would have to walk miles just to transact with people, from rural villages. But they did have a mobile phone, so they could, in theory, make payments. So imagine then if the switch can process a debit-credit payment. Payments are just debit credits, double entry accounting. Imagine if the switch could do that with, say, one database query instead of 10. Then you could trade this performance to reduce fees and then enable people to make payments who couldn't otherwise afford it. So we were brought on as consultants, see where the performance bottlenecks are. First thing we did, let's spin up the switch. We start sending payments in, and then we trace all the SQL queries, that happened as you make one payment, again, to see where the bottlenecks were. What we saw here was interesting. So for every payment, there'd be a SQL transaction. Within the SQL transaction, there would be around 10 SQL queries to process business logic, and this is if the switch is perfectly optimized. So one transaction, and in that there's 10 queries going back and forth across the network while the transaction is holding row locks. So the accounts between which the money is moving are row locked the whole time while information is flowing back and forth across the network. So if another payment came in, the performance would tank. So in other words, the switch was taking a general purpose SQL database, and they were then writing a whole lot of code around it to build the equivalent of a debit credit database. And they were, again, moving the data to the code instead of moving the code to the data. So we asked the question, what if you could redesign the database as a financial transactions database? Instead of processing 10,000 debit credits, imagine you have 10,000 debit credits that you want to do. Normally it would take 100,000 SQL queries because for every one, it's roughly 10. So instead of processing 10,000 debit credits with 100,000 queries, what if you could process 10,000 debit credits with a single query? So one query to the database, 10,000. Another query. This was, the 1000x performance trick that led to the creation of Tiger Beetle. So people don't, when we say, 1000x OLTP performance, they're like, can you say that? Where's the benchmarks? And we're like, well, we don't want to be negative. We'll tell people how we do it. Let them understand from first principles. It's a simple idea. It makes sense. Not blind with benchmarks. We have our own benchmarks of the performance Tiger Beetle can do. But really, this is the 1000x trick. It's actually a 10,000x trick because we put 10,000 in one query. And then we take 10x of that and put it aside for safety techniques. But it's nothing special. It's nothing special. We just redesigned the database for this domain. It's almost embarrassingly simple. So instead of processing, again, 10,000 debit credits with 100,000 queries, put them into a 1 meg message and do one round trip. So this way you amortize the cost of fsync, how you get durability as a database to disk, and replication. So Miles Davis, he said that a painting is music you can see. Music is a painting you can hear. And with Tiger Beetle, again, we had the freedom. We could sketch, and then we could paint from first principles to find, what we thought that this looks like a global maxima. It's a 1000x global maxima. But I think the most surprising thing about all this is not this performance secret. So we found the key to performance that we needed, how to make the switch so much faster. The surprising thing is we didn't stop there. We could have, but nevertheless, we made the unconventional decision, at least from an engineering perspective, to write everything from scratch to be close to the middle. So we had the big idea, and then we went and looked at all the little things. And I think that's really surprising from an engineering perspective. You've got the big thing. Why do you need to go do all these little things? So we did, we wrote everything to be close to the middle from scratch. So network protocol, storage engine, consensus protocol. And we decided back in 2020, 4 years ago, we were going to invest in a systems programming language, not of the last 30 years, C or C++, but in what we felt would be a systems programming language for the next 30 years, Zig. So we picked Zig because when you're building a database, memory bandwidth is often your bottleneck. So we wanted to use techniques. Again, these are all the little things. Techniques like zero copy, zero deserialization, most of all static memory allocation. So I'd spent 10 years by this time in Node.js and had seen how hard it was to build a reliable program, that you run in production. It's one thing to just write a program. It's another thing to operate it. And I found this just so hard in Node.js. It was really hard. You had unpredictable GC pauses and anything could allocate from under you and exhaust memory. So when it came time to Tiger Beetle, we wanted it to have explicit limits on everything, handle overload, and not panic in production. And Zig, of course, made allocating memory and handling errors explicit. So I/O U-ring had arrived on the scene. We could reduce syscalls and context switches. Again, all the little things. And I want to get you wondering, why did we do this? Why did we focus on all these things? But with I/O U-ring, we could have a single-threaded control plane, nice async I/O, make the kernel our thread pool. And we wanted to see how far can we push a single core. We've already got the 1000x performance trick, and here we're trying to optimize single core performance. So again, from an engineering point of view, these performance techniques, they added a few percent here, a few percent there, and they took time. Because on top of these design decisions, and this is why I loved Zig, is we adopted a zero dependencies policy, so no dependencies. So we made a set of surprising decisions, at least for me. We picked Zig. Instead of RocksDB, we wrote our own storage engine, Tiger Beetle's LSM forest. Instead of Raft, we implemented ViewStamp replication, and we ran as far away from GC as we could, past dynamic memory management, even past manual memory management, malloc and free. We just ran so far and ended up at, in arms of static memory allocation. So probably the only thing we didn't do is write our own programming language. That's what Andrew would have done. But actually, by the way, it's this is what Foundation DB did. They wrote Flow over C++. So we were employed at Coil at the time. They sponsored the work on Tiger Beetle. They later invested in Tiger Beetle, like I said earlier, when we spun out as a company. And I think looking back, the amazing thing about all this is that we would share these wild design decisions from an engineering point of view on our all-hands calls. And our CEO at Coil, Stefan Thomas, he wouldn't even blink. He's like, you got this, you know. So we had a high-trust environment, and our managers would encourage us, you know, follow your excitement, follow your nose. So they understood the big idea, and this is the thing I want to share with you now. And it's this. So engineering alone would not have justified all the performance techniques that we invested into Tiger Beetle. Engineering alone would not have led to this kind of engineering. But business did. And that's because Tiger Beetle was created to serve a need that we saw, the need for more cost-efficient payments. So every percent mattered. There was a business case for it. But the other business reason, also, you know, the reason why we picked Zig and static allocation, this is the other part of the business reason, was just because it was easier. So, and I think this is also surprising to hear. How can it be easier, you know, to have zero dependencies, to own your storage engine and consensus? Why is that easier to write everything from scratch? Again, from an engineering perspective, these are probably some of the most difficult design decisions that you could make. These things take years to build. And in the software world, it's also common, you know, there's pressure the other way, because so often we see development of software as an expense, not an asset. So people say things like, you know, developer time is expensive. Try and optimize, you know, how long it takes to create something. But I think, unfortunately, when software is seen as an expense like this and not as an asset, then what happens next is that there's pressure from managers to ship faster to save on costs. But the big problem is that this forgets the relationship that the makers have with the users. So where the developers could have spent a week or two extra to think a little bit harder and release better software, to pay this cost once and for all, now the users have to pay this cost in production again and again for every user. And so it's not good business, I think, because it optimizes only for one side of the relationship instead of for the relationship as a whole. So it would be cheaper for the world if someone spent 10% more time to release something that's 10 times better, enjoyed many times over. And as Henry Ford, you know, someone who had the same vision once said, I will build a car for the great multitude. It will be large enough for the family, but small enough for the individual to run and care for. It will be constructed of the best materials, but it will also be so low in price that no one making a good salary will be unable to own one and enjoy with their family the blessing of hours of pleasure. So he was thinking of the whole relationship, the cost of ownership. And this is why we realized it would be easier to make hard design decisions, because we weren't only thinking in terms of how easy it would be to develop Tiger Beetle. That's very easy to do, you know, make it easy to develop. The more important thing is to think of how easy would it be for our users to operate Tiger Beetle in production, so to have a rock solid experience. And there's a beautiful business term for this. It's called TCO, or total cost of ownership. So total cost of ownership asks the question, what's the cost, not only to the makers who develop the software, but to the users who run it? And I believe it's one of the most powerful business incentives, bigger view of business, to crafting high quality software. Because the world tends to reward businesses as a result of serving a need and serving it well. So TCO is the thing that will allow you to do things that engineering alone would not have signed off on. And to be clear, total cost of ownership is not only about the cost to the users, which is the beauty of TCO, in that you're also thinking of the relationship. So it also includes your own costs of production. So you want to serve, it's okay if it takes a little longer to ship quality, but you also want to think of how you can optimize your cost of shipping. So with Tiger Beetle, we did something different in how we developed the database. Normally, if you're writing a consensus protocol from scratch, 5 to 10 years to shake out the bugs. Storage engine, much the same. And these things are so hard, they're still going to have bugs. After 5 to 10 years, you've only just started shaking out the bugs. And this is not great. if you're processing people's money, because that's close to nuclear. So therefore, we had to think differently about engineering our methodology, and especially with regards to safety. So we created a methodology called Tiger Style. Before we started coding Tiger Beetle, the first thing we engineered was the methodology, Tiger Style. Not only to adopt NASA's Power of 10 rules for safety critical code, and we weren't going into space, but we were going to enforce things like static allocation, and we were going to put 6,000 assertions into Tiger Beetle, but also to find a way, this is what we wanted to do, how can you test and simulate the database in production? How can you optimize how easy it will be for the users to operate? How do you test that? And how do you shake out the bugs autonomously instead of manually? So this is kind of like autonomous testing, before AI was a thing, thanks to Foundation DB who pioneered this technique. So it's almost like learning to fly a plane. If you have a flight simulator, you can experiment, you can learn faster, because nobody gets killed when you crash the plane. So in other words, if you can design a database to run in a simulator, then your users don't have to pay the cost of opening issues each time they find a bug, because you found them already. So instead, you try and simulate, all the different ways that the network can fail, or the disk can fail, or processes can crash, and you inject these faults into your database, and then you also check that everything works correctly. So because you simulate the whole world, you can actually check the state of the virtual processes as you inject events. It's very powerful. It's almost like chaos engineering or Jepsen, if you're familiar with these, but it's not. Two reasons why. First difference is that we designed Tiger Beetle to run not only in a simulator, but also in a way that we could abstract the source of time in Tiger Beetle. So this is the clock, the intervals, the timeout. So often we think of testing and mocking things, like we mock Postgres, or just generally speaking. But how often do we think of mocking the source of time, your clock, all your timeouts, your timers? So this is what we did in Tiger Beetle, like Foundation DB did. So in other words, we could turn the simulator into a time machine. Because we abstracted time, the simulator could then speed up time in a while-true loop while injecting faults. And we could speed up time by a factor of roughly 700 times. So 1 second of simulator time can find a bug that will otherwise take 10 minutes in the real world to find. 1 second, 10 minutes. And you're just getting ahead and getting ahead. I think there's 3 databases in the world that use this technique, and it's so powerful. It's like a movie. You can speed up time, see if it has a happy ending. The second difference, it's also like a movie. If you find a bug, you can watch it again and again and again. It's a movie, so the way it's deterministic, you get to think, oh, we crashed before the ending. Let's replay this scenario. But you can replay it while you're putting in printf statements. So if you're like me and you still do printf, I think this justifies printf debugging. When you have a simulator like this and you can replay things. So we wrote all the code to be deterministic. And here's the big reveal. We could do this because we didn't have any non-deterministic dependencies. We didn't have any dependencies. So we could be sure, we could guarantee that everything in Tiger Beetle was deterministic and could be tested like this, that we can replay the movie again and again. So we could shim the network disk, the clock, and we could ensure that Tiger Beetle's code always executes the same way every time to debug quicker. So moral of the story or principle is working harder, taking longer, even with our design decisions, didn't in fact take longer in the end, because deterministic simulation testing gave us a way to speed up time. So you go slow to go fast. So for example, in the first 3 weeks of switching on the simulator, we were able to find and fix 30 distributed systems bugs in 3 weeks. Find, fix 30 bugs. Each of these on their own would probably have taken months to find and fix without one of these simulators. So if you want to learn more about how this all works, especially the simulation testing, come and join Matt Clad. He's live every Thursday on Twitch, and we've got a fun show called Iron Beetle. And Matt Clad takes you through the code and talks through it. So it's been less than 4 years. Tiger Beetle's first production release was in March. We've actually got something here for you afterwards for about if I don't know how many fed. 20. Okay, so we've got a bit of production release here. Come and chat to us afterwards. But we were just lucky that we had the business backing and the business patience, the business wisdom, from our managers, so that we could take our time, not cut corners. We could implement all the safety techniques and research we knew. So we really tried hard, to make Tiger Beetle the fastest, safest database we could possibly have built. So perhaps, I'm sure others could have done better, but this was our best because we did it for the users. So we have a saying on the team at Tiger Beetle, BTHF. Anyone guess what it stands for? Build trust, have fun. Because software you can love is software you can trust. And beyond trust, it's about fun. So you build it once, but your users delight in it again and again and again. So let's play a little music. I want to show you something we made. In the words of James Brown, let's play it live. So this is actually Tiger Beetle. It's never been in a cinema before, but this is the premiere of the distributed database in the cinema in Milan. And this is the simulator. And this is the cool thing, is that when you have all these ideas at play, you can save time. And then I met Fabio Arnold here 2 years ago at the Milan party, and I showed him the terminal version of our simulator, and I said, it would be cool to work together, and maybe we could put a front end on this, because how do you show kids? This is my goal, just how do you show kids a distributed database? And so this is what we came up with, and we've had a lot of fun, just to try and show you Tiger Beetle running virtually in a simulator. It's in WASM, thanks to Zeg, running in the browser, in a cinema. And what we've done is created 3 different scenarios that are simulated, 3 different movies. Milano, Red Desert, Radioactive. And Milano is really easy. Everything is chilled because you've got your espresso a day, your pizza a day, your gelato a day. The network is perfect, disks are perfect, processes never crash. Let's see. And what you're seeing here is a cluster of 5 Tiger Beetles. They're busy starting up, so they look a bit bandaged. The cluster is about to start up. And up top, we've got 3 agent Smiths. Those are the clients. They're going to send network requests into the distributed database. You can see Captain America as the primary. And requests are going to come into him, and then he's going to replicate it to the cluster. And there they go. So requests are coming in, getting backed up, and everything is okay. There isn't a Mexican standoff there. It's a decent behavior. And what you can also see on the left is the seed. From this number, you can replay this movie again and again and again. We've got 5 replicas, 3 clients. Network is perfect. The disk was perfect. And that was too easy. So want to level up? Okay. Red Desert. What we're going to do now is just break the network. So there's going to be packet loss and more latencies. And this is, we're going to replay messages, partition the network. This is usually as hard as it gets for databases. Just breaking the network and testing that everything works. And the simulator is checking, that everything's working correctly. If it isn't, it's going to crash. So the fact that we're live is everything is working. We can also take a hammer and sort of poke the simulated world. There we go. Crash that beetle, and it comes back up. But let's crush another one. The hammer is my favorite. After that, you can put a beetle in a box, like Mission Impossible 5, cut it off from the network. And you can also zap it with a cosmic ray, which we won't do, because no one ever does that, right? assist crash beetles. So we survive. And this is, again, this is as far as most databases get tested. This is what Jepson would do. And it's very hard to pass this test. But let's get radioactive. Okay. So this is how we normally do things at Tiger Beetle. We write, let's just put in 8% corruption on all the disks in the cluster and check that it works. Because it's for the users. It should be like ZFS, almost as awesome if we can, So on the read path, we're going to corrupt 8% of reads, 9% of writes, and the simulator is going to do this. And the simulator knows I've put in so much corruption, the cluster should be perfectly available. Or I've put in too much corruption, okay, now we have to shut down. So it can actually check not whether the code's correct, that's easy, but are we taking the durability that we've got from the replication and are we maximizing that for high availability? So disks fail and Tiger Beetle's detecting that and repairing. What's cool about this level is that there's a little Easter duck which will engage duck mode. So credit to our friends in the OLAP world, DuckDB. And you can see, what is an OLTP database like Tiger Beetle? How does it handle being crashed by a duck? And it survives, I think. Okay, and this is actually my favorite tool, is the Cosmic Ray. Zap the disk and check that everything survives. And this is just normal, but it's actually not hard to do because you've just simulated all of this. So things that were so rare, like disk corruption, 1% in a 2-year period per disk, we just make this an everyday thing so that we can check that the code survives. So just want to say a huge shout out to Joey Marks. He's done the art also for Cycle. He did the art for this. Fabio Arnold, who's here. Huge shout out to the two of you. You were stars. Like, they've created everything that you see here. So, and these are, Adrian was one of our managers who always said, back yourself, follow your nose. And just want to encourage all of us here today, keep on doing that to make software you can love. Yeah. Great.
Thank you very much, Joran. So that was a great talk. Thank you. Let's have a couple of questions from the audience, and then, if you don't mind, I actually have a couple of questions of my own. So let's see. Any raised hands that I can see? Yeah.
Hey, so I have a question. Why is this not called building a business you can love, but it's called Biodigital Jazz? So what's the backstory
for Biodigital Jazz?
Biodigital Jazz, yeah.
It's something like Tron is one of my favorite movies. And so Kevin Flynn, the programmer, says it in Tron. And as it's happened, most of the talks I give, I always somehow slip in a Biodigital Jazz reference. And I figured, well, there should actually be a point where the talk title is just Biodigital Jazz. So bio, is people and business, digital is software, jazz is art. And I thought that's the intersection of all these things.
Hi. I have a question about the simulator. So isn't it like just a step before a theory improver? Because I would assume like if you could prove that all of your algorithms are correct, then there's no need more for the simulator, but the simulator is probably more practical.
Oh, great question. So with distributed systems and consensus protocols, there's a lot of formal methods. And this is where you take the protocol specification before it's coded. You just take the protocol and you prove, is it correct? Is the design of the protocol, could it work if we coded it? And it's an amazing tool which you want to use, which is great. It lets you design and prototype protocols. The challenge though was we were thinking of total cost of ownership. So it's one thing to test that your design could work, but most of all, you want to think, how is this going to be in production, the final code? How do we apply these model checking techniques to the actual code? Because, it's one thing to go from a specification like the architect's blueprint to an actual house that users are going to live in. How do you model check the house? And so that's what the simulator is doing. It's taking the models that we've got of how things fail, and it's model checking them, but on the actual code. So that's why it's so powerful, because it's like end-to-end testing, thinking of total cost of ownership.
But do you still use theory improvers in the beginning just to...
Yeah. So the nice thing is that view stamp replication, if you know of Raft is almost exactly view stamp replication, which is the pioneer, and they have all already been formally proven. So we knew the design worked. Now it was a question of how do we know that our code is going to work? And that's almost the next step. So you can use both techniques. If you're trying to create a new protocol from scratch that isn't in research, formal methods are great because you can design quickly and you can communicate the design precisely. And then the second thing you want to do is, now you've proven that it could work, how do you know that it does work? And that's where you'd want the deterministic simulation testing, or DST, which is a newish technique. So Foundation DB pioneered it, and it's still, a lot of it till now has been chaos engineering, but it's not deterministic, can't speed up time, can't replay time. Good question.
Next question.
Hello. So great talk, great demo as always. So I have two questions about simulations. Is it based on discrete event system simulation idea for like network testing? And then how do you model your faults? What distribution did you pick, and how representative are they of actually what happens in real life?
Yes, so we didn't come at it from discrete event simulation. I actually am not so, I wasn't aware of that. I was aware of Foundation DB and Dropbox, just how they were doing this practically. And I guess it's very similar. The thing we were trying to do is not just the network, but also the disk. What was very new at the time was storage fault research from Wisconsin-Madison University. As new as 2018, they had research papers showing that most distributed systems didn't have a storage fault model, so they weren't modeling, how disks fail. So Paxos and Raft, they're only correct, the formal proof only holds if you assume that disks are perfect, but they're not in production. So those were, that's where we came at it from, was the angle of Foundation, Dropbox, and the Wisconsin research. And then in terms of how do we do distributions of probabilities of the fault models, so we've tried, there's the recentish paper called swarm testing. We've tried that, where you're not fully random across all your faults all the time. You do mostly normal and then some faults, and you constrain that. That's quite interesting. But there's a lot more that we can do around, like, not just randomness, but going beyond that. There's going to be a conference in June, which Larisse will speak to. I'm not allowed to speak to it, but Alex Petrov, the author of O'Reilly Database Internals, he's on Apple's Cassandra team, where they also do DST. He's going to speak to this. His whole talk will be about going beyond randomness. How can we get good distributions? So this is something for us. It's like an open, it's what we want to do next. More and more, be more tricky,
Very cool. Thank you.
Thanks, Jakub.
Any more questions?
So with the simulator, is radioactive right at the edge of what tidal butyl can survive, or like how much farther can it go? Because I've never seen it fail in the simulator, but theoretically it can. I'm just kind of curious.
Yes. Yeah. I didn't see where you are. Could you raise? Okay, great. Yeah. So that's what the simulator does. Is chaos engineering the system under test is a black box. So you don't know how far the system can go. You don't know what the limits are, before you've pushed it too far. With the DST, you control the whole simulated world, but you also know the system that you're testing. And you can even hook into the code, the actual code as it executes. So you start to get a feeling for how far you can push the system. You can push it to the theoretical limit. So these protocols will have, they can survive F faults. And then the simulator will push Tiger Beetle up to F faults, and check that it remains available. And it is protocol aware. It knows it's not black box, but the simulator understands consensus. It understands our storage layout on disk. It'll even check things while Tiger Beetle operates. It'll check that our user space page cache is coherent with disk all the time. Because even the Linux kernel page cache can sometimes not be coherent if you have storage faults. There was a paper on this called Can Applications Recover from Ipsing Failure? So the kernel page cache is not always coherent, but we will test that Tiger Beetle's page cache is always coherent. You can be very protocol aware. So we take it to the limit. Then we don't always push it past because things would break. But it is useful to push it past because you want to know that you handle faults by shutting down. So that's the golden rule: is you should be fault tolerant up to the number of faults that you replicate for, and beyond that you must shut down correctly. So both are important. We test that in different ways. Yeah.
I think Tiger style is pretty cool, but I feel like most software projects are not, nearly as critical as something in space or something doing financial transactions. So I'm just curious, how widely applicable you think it is. Like, do you think other people should adopt it, or are there other things people could design for different domains like that?
Yeah, thanks. I think the main thing is always just thinking of the relationship. It's not the development time only, but it's the user experience in production for any software. So software you can trust, software you can love. How do you optimize total cost of ownership across the relationship? And if you have that principle and that purpose in mind, it'll guide you when and how much. Doesn't have to be binary, but how much you do. I do think though, assertions and static allocation and deterministic simulation testing. Well, let's just do static allocation. That's so valuable, not because of all the safety or performance techniques. The number one benefit of that is it's a mechanism to force you as the engineer to think through everything. And I think software breaks because we don't think enough. We just have to think an extra day and it'll get much, much better. So static allocation forces you to confront all the limits. And I actually think it makes software engineering quicker, because I think the reason software takes longer compared to real world engineering, we really struggle to put estimates on a software project. Real world engineers are a bit better at this. And I think they're better because they have physics, they have physical constraints, which we lack in the invisible world. But as soon as you bring in like Tiger style or static allocation and limits, you start to have physics and you get better at thinking. And I think so you do go slower, but with the testing, you go much, much faster. So you net, I think you actually are quicker. And probably, any kind of software would benefit if you do want to have that deep understanding of the physics of how the software works. It's fun. It's actually really, really nice. Coming from Node.js, I struggled with so many things, and this was the antidotes.
Thanks. Awesome. So now I would like to ask a question about more the business side. It's a bit of a hardball question, so I'll preface it with some praise. There's one part of your talk that I really liked that actually caught me by surprise, which was your reasoning about how some of the engineering work in Tiger Beetle, if it was just engineering work for the sake of engineering work, it wouldn't make sense. But what made sense was the fact that you envisioned a business need for it. And I think that's real, right? You work at a software project for a company and maybe you want to make certain things better, but business priorities are different. And in the end, your boss isn't even all that wrong in telling you, listen, this optimization work that you're doing right now, leave it there. It's not that important. And in the case of Tiger Beetle, I am also personally genuinely interested in seeing Tiger Beetle and more in general the Interledger Foundation and like also what Coil was doing. I would like to see new business models come out of faster payments. I run a YouTube channel and I find it insane that if I want to get something back from people watching my videos, the only way I can do that is let Google put weird frames in my videos. That's ads. And it's weird, right? Because you don't like ads. And I wish, like, it would be nice if there was an easier way. You can do Patreon and similar things, but those tends to be things where, like, you like the creator a lot. While instead, it would make sense that even if you don't like the creator a lot, you had a way of, like, pitching in just, like, a fraction of a cent. But these are things that can't exist today because 15 cents, I believe, is, like, where you start when paying from PayPal. Like, that's the fixed price of a PayPal transaction baseline, something along those lines. So, yeah, I would love to see new business models come out of this. That said, Tiger Beetle is a startup. It got venture capital money, and venture capital money is, it is not a secret that startups want to get an exit. And an exit in the end is, like, quite literally ending the relationship. And sometimes that can be done also in a bit of a rough way, right? You end the relationship, you throw out all your other person's stuff out of the apartment, lock the door. I don't want to ever see you again. So how are you going to avoid the bad ending?
Thanks, Teresa. I love the question. It's not that hard.
Okay.
So I think the way I came at Tiger Beetle was there were a lot of experiments that I had done before.
Mm-hmm.
And they were, personal experience. And this was you wanted to build this kind of thing. And then we got the chance to do it. But I thought this kind of technology, it's so valuable that it has to be open source. It's too valuable not to be, because, if I wasn't at Coil anymore or wherever, I want to be able to use Tiger Beetle and use our VSR framework to build new, like, distributed applications and to hack with it. So it had to be open source. So I think that enables, like, whatever happens to Tiger Beetle, the company, it's open source. The other thing is that the copyright for much of the code is assigned to the Bill and Melinda Gates Foundation, so we can't relicense it. We're committed to Apache 2. And then the other part of it is just you've got to be good at business. So you want to have good investors, be able to choose people who think the same. So there's two kinds of, I think there's three kinds of exits. The first two, the bad one is the acquisition, because you've almost failed to serve the world. If the world has got a big need, you don't need to be acquired. So it's more if you fail to serve that need. I mean, sometimes there's an acquisition is a great successful outcome for some businesses, but depending on your business, maybe you don't want to be acquired. The second one is like an IPO, but that isn't really an exit. It's just a liquidity event. So that just means that your paper money is now actually on the stock market. So you don't have to sell it or not, or you can sell some, but now you're a public company. And then I think the third one is where you build a great company. That IPO is sort of the first step, and then you're now around for a long time. But then it's so critical that you have to have good, healthy business thinking, to think, like people like Henry Ford, Thomas Edison, the founders of Hewlett-Packard, IBM, like they all built great companies and they lasted beyond the initial founder. How do you do that? And then it comes to things like culture. So what's the vision? Are you here to serve society, to serve a real need? Do you understand business like that? So often people don't. We're short-sighted. So the vision, the mission, are you building trust? And then the values of the particular company. How do you, because a business it's about people, it's relationships. And are you hiring the right kinds of people? Yeah. Did I answer your question?
I think you did, yeah. I guess that some of it is very similar to the advice that I also give to people when they ask me about how to get better at Counter-Strike. And the answer is you need to click heads. Get good at clicking heads, and that's how you win a Counter-Strike. Mm-hmm. So in a similar way, you gotta get good at business. And yeah, I agree. Yeah, he said a little bit more than that, but at its core, it's like it's a mechanical part of reality. Yeah, that makes sense. So that's awesome. I have one short story that I remember telling people in April at the Milan party, but I don't think you were there. So just in case you never heard this story, and also for the benefit of the people who weren't there at the time, so this is a story. So just like I think it's healthy to be a little bit skeptical of startups, venture capital, and all that stuff. But also the extreme opposite has a very big number of issues. There's one story that usually blows people's minds when I tell it. So how many of you have used the GIMP? So the open source image editor. Okay, keep your hands up. Keep your hands up. So pull your hands down if you don't like the user interface of the GIMP. Okay. Almost everybody. Okay. So you can fact check what I'm about to say by going on their official blog and read all their entries. But the GIMP project, up until August of, I think, 2018 or something like that, was not able to accept donations to pay developers. They were able to accept donations, but they never set up a proper financial entity to get money, so they were piggybacking off of the, I think, the GNOME Foundation. And for one reason or another, the only way they could use the money that they received from donations was to set up events and to buy hardware for developers. But they could not pay development hours to software developers. So now that you know this, can you imagine what a miracle the GIMP is? And at the same time, what a shame. Had they done the proper work to properly pay software developers and set up a financial entity and like get the business side right, the GIMP today would probably be 10 times better than what it is, even though it's already, in my opinion, a great achievement. So, I don't know. Do of that what you will. So, thank you, Joran, very much.
Thank you, Luis. Yeah.
Yeah. Okay, so now we're going to go on a break, and we're going to start in about 10 minutes. Thank you.